As we embark on a new section on advanced trigonometry, we need to make sure that some of the fundamentals are in place. So in this session, we're just going to have a start by looking at the unit circle and a particular sum of the exact values and how we can derive them. So first of all, we've got a right angled triangle here. You can see that we've got an angle theta with three sides A, B, C, and three angles A, B, and C. First of all, I would like you to find an expression for A and B in terms of theta, and then try and use your answers to find an expression for tan theta in terms of theta. So let's have a look at this. First of all then, the expression for A and B in terms of theta. So if we have got theta here, we know that sine theta is going to equal opposite, which is adjacent over hypotenuse, which is C. We can rearrange that to give us an expression for A in terms of theta, which is C sine theta. Similarly, for cos theta is going to equal adjacent over hypotenuse, which here is B over C, and we can rearrange that to give us B is equal to C cos theta. Use your answers to find an expression for tan theta in terms of theta. Well, tan theta is going to equal opposite, which is A, over adjacent, which is B. We have an expression for A and B, so we can say, therefore, that tan theta equals C sine theta, which is the same as A, divided by C cos theta, which is the same as B. The C's will cancel out and leave us with tan theta equals sine theta over cos theta, which is one of the general rules that we will be working with a lot in this unit. Right, next up we're going to have a look at the exact values in a series of special right angled triangles. So there are some tricks and tips you can use to memorize these exact values, but it's much better if you can actually derive them and understand where they come from. So in this first instance, we have just got a right angled triangle with two sides 1. So this is an isosceles right angled triangle, which means that obviously these two angles here have to be 45 degrees. So the first thing to have a look at then is the exact length C. How can we find that? And then use that to help us find the exact values sine 45, cos 45, and tan 45. So have a go at those. The exact value for the length of C is just going to be found using Pythagoras, which is in fact root 2. The exact values are sine 45, so it doesn't really matter which of these you use, but sine 45 is going to be opposite 1 over hypotenuse, root 2, or here, opposite 1 over hypotenuse, root 2. Cos 45 is going to be exactly the same thing, so cos 45 here equals adjacent over hypotenuse, or here, adjacent over hypotenuse. So these two will have the same value. Finally, tan 45, opposite over adjacent, or opposite over adjacent will give us 1. So these are three very important values. You'll see here that even though I've written sine 45 equals 1 over root 2, which that is the exact value, I could rationalize the denominator and express it as root 2 over 2. Both of these are correct. The next triangle we're going to have a look at is this one here. Now imagine we've got a equilateral triangle of side 2, which would make this angle 60 degrees, but then I've put a perpendicular bisector down the middle. So therefore I would have a hypotenuse of length 2, this base here of length 1, this angle here would be 60, and if I've put a perpendicular bisector, this angle here would be 30. So bearing that in mind, can you try and find the exact length of A and the exact values here? So the exact length of A is going to be found using Pythagoras again, so we're going to end up with root 3. These are our two angles, or three angles, so to find the exact value of sine 30, that's going to be opposite, which is 1 over hypotenuse, which is 2. So we're going to have sine 30 equals a half. Cos 30 is going to be adjacent over hypotenuse, or root 3 over 2, and tan 30 is opposite over adjacent, which is going to be 1 over root 3, and again I've just rationalized the denominator here. The exact values for sine 60, cos 60, and tan 60. So sine 60, again, opposite over hypotenuse. Cos 60, adjacent over hypotenuse, which is a half, and tan 60 is opposite over adjacent, which is just root 3. So these then are the values that you need to be familiar with. So ideally, you just need to remember these two triangles. So isosceles right angled triangle of side 1, or you've bisected an equilateral triangle of side 2 to give us this. And in this instance, you can then work out all of these exact values without having to memorize them, which is probably a less reliable form of getting the exact values. Right, let's have a look at the unit circle now and see how we can use some of these values. So let's start with, we've got a circle here. We're told here, so this coordinate here we're given is 1, 0. Because it's a circle, we know the radius therefore is 1. We're given a point on the circumference here, which has coordinates x, obviously this distance here, and y, this distance here. When we use the unit circle, we measure angles which start from this 3 o'clock position, and we assume that counterclockwise is positive. So what I want you to have a think about is how you could find an expression for x and y. So this would be obviously x and this would be y. How can we find an expression for those in terms of theta? So if this is theta, we know that cos theta is going to be adjacent over hypotenuse, which here would be the x coordinate over the hypotenuse, and we can rearrange that to say that x equals r cos theta. Similarly, sine theta equals opposite over hypotenuse, which here is going to be the y value over the radius, which we can rearrange to say that y equals r sine theta. Because it's a unit circle, we know that it has a radius 1 unit, so r equals 1, and we can therefore say that x, because these two values are going to be 1, x will represent cos theta and y will represent sine theta. To find tan theta, we know that that would be opposite over adjacent, or y over x, and we've already seen that y is sine theta over x, which is cos theta. So again, we're seeing this relationship, tan theta equals sine theta over cos theta. So for any point, anywhere on this circumference, we will know that the x-coordinate will tell us the cosine of the angle, and the y-coordinate will tell us the sine of the angle. We are also able to establish that because we've got a right-angled triangle here, we know that x squared plus y squared must equal r squared. And we've said that as the radius is 1, we can generalize that to say that x squared, which we're saying is cosine theta, so cos squared theta plus y squared, which we said y is sine theta, so sine squared theta is going to equal r squared, which equals 1. So we end up with this rule here, cos squared theta plus sine squared theta equals 1. And this again is a very important rule that we will draw on throughout the next series of sessions. Okay, so if we had a question like this, find the exact coordinates of point D and give it to 3 significant figures. So for this, if we wanted point D, we would know that the x-coordinate would be cos 59 and the y-coordinate would be sine 59. Those are the exact coordinates. Plug them into your calculator to find them 3 significant figures, and that would give you 0.515 and 0.857, noting that that's 3 significant figures. In the diagram, find the exact coordinates of point B. This is why we need to know our exact values, because the x-coordinate will be cosine 30, which we know is going to be root 3 over 2, and the y-coordinate is going to be sine 30, which we should know or be able to work out is a half. So we can also use this, for instance, we can make connections here with the ambiguous case. We've got a diagram which shows point B with an angle of 30 degrees and point C at an angle of theta from OA. Find the value of theta, and what are the coordinates of point B, and use the symmetry of the unit circle to write down the coordinates of point C. So let's take this bit by bit. The coordinates of point B we've just established in the previous question at root 3 over 2 and a half, because the x-coordinate is cos 30 and the y-coordinate is sine 30. We know that C, this is symmetrical, so the exact coordinates here, this is going to be 180 minus 30, which is 50. So the x-coordinate is going to be cos 150, and the y-coordinate is going to be sine 150. We should also recognize that the y-coordinate here is the same as the y-coordinate here. Yeah, so the sine 30 and sine 150 will have the same coordinates. We should also recognize that the x-coordinate here is just a reflection of the x-coordinate here in the y-axis. So therefore, cos 150 will just be negative cosine 30. More generally, then, we can say that for supplementary angles, alpha and beta, the sine alpha equals sine beta. So here we've got 30 and 150, so the sine of those two angles is the same, and cos 30 is the same as negative cos beta. So this is the relationship that we can look at more generally. For any angle theta, sine theta equals 180 minus theta, so sine 30 equals the sine of 180 minus 30, so we said that was the case here, sine 30 equals sine 150, and cos theta equals negative cos 180 minus theta, which is also what we looked at here. Here we've got a unit circle with a line drawing through it. If we want to find the gradient, that is going to give us the, we'll be able to find that from the tangent of theta, the angle that that line makes with the unit circle. We know that with Pythagoras, sine squared theta plus cos squared theta is going to equal 1. The gradient is going to be the change in y, which is going to be sine theta minus 0, over the change in x, which is cos theta minus 0, which is equal to tan theta. These then are the key properties from this session. Sine squared theta plus cos squared theta equals 1. Tan theta equals sine theta over cos theta. And for any line y equals mx, which forms an angle of theta with the x-axis, the value of m, the gradient, is tan theta. A couple of quick examples here, and then we'll look at some more examples in detail in the next session. Find the gradient of the line which forms a positive angle of 130 degrees with the x-axis. So the gradient here is just going to be sine theta over cos theta. So we can calculate that. Well, here we can use a calculator to give us negative 1.19. If we're asked for exact values here, we can't find out what 130 degrees is easily. So that's why we're going to be using the calculator. Find the gradient of this line. So here we're going to be able to find out the exact values, because that's going to be, this angle here is going to be 120. So therefore we can say that tan 120 is sine 120 over cos 120, and that's going to be the same. Sine 120 is going to be the same as cos 100, sine 120 is the same as sine 60. We know that from the previous rule, which is just root 3 over 2. Cos 120 is going to be the same as 60 degrees, but the negative of it. So we know that cos 60 is going to be a half, therefore this should be negative a half, and we can simplify that to give us negative root 3, or negative 1.73.